introduce you then to this afternoon's session. First up, we have a presentation from Husni Habal on machine learning based structure recognition and analog schematics for constraints generation. Sounds great. Let's move on and we'll go straight to you, Husni. Okay.
Thank you very much. So I should share my screen, correct? Okay. So thank you very much, Mark. Hello, everybody. Hopefully you can hear me. So I am in my company's central analog design methodology team. Yeah, we typically work on well, analog design methodology topics. So I would like to begin this presentation with just an introduction to this under problem statement. Why are we interested to look at analog structure recognition? What is the purpose? Then I will look at the how we do our pre-processing. What features or information do we extract from a circuit or a schematic or a netlist? And how we process this information for the next step, which is our design flow, our structural recognition flow. And in this, I will just focus also on two main steps, which is our regression model and the graph convolutional neural network. And I will finish with some results and the conclusion. So at our company, at Infineon, we use a constraint-driven analog design flow. That is, we use constraints or rules in a formulated manner to control or to convey information to our automation tools, whether they are vendor tools or in-house scripts or programs, or to our designers, or usually the physical designers, such as the layouters. So these rules depend on, are usually dependent or specific to each type of circuit structure. And these could include, like I said, rules for physical design, placement and routing. They might be electrical or geometric rules that the designer uses, or if we're using an optimization algorithm for circuit optimization, they will be used there. We also use these constraints to tweak or set our simulation and analysis settings, like, for example, by simulation, and to add or remove verification checks. And I give a small example here. The most basic structure you could have, maybe in an analog circuit, is a matched differential pair. This is usually very sensitive to mismatch between the devices. And typically for placement, you would put these blocks in a common centroid or symmetric placement. You'd add dummy devices around them. You also have to make sure for when you're doing circuit sizing that the widths and lengths are equal, maybe that the DC operating node, like the gate to source voltages, are nearly equal. In terms of simulation settings, you might decide that I have to add a mismatch analysis once I see that I have such a structure. I might also add a verification for an aging effect. So if you have a PMOS differential pair, as shown here, it's susceptible to negative bias temperature instability, etc. So this is why you want to know these structures. Yeah. And for the scope of this, our input can be a simple circuit block at the transistor level and can go all the way up to a whole IP, which has some nested hierarchy of subcircuits. And for this constraint-driven design, all the structures, functional blocks in different levels of hierarchy must be identified. For this DVCon paper, I'm going to restrict myself to the most simple structures, which we call here as level 1 or level 2 structures, and just show them on top of this like transistor level circuit, which I think was a comparator. Yeah, so you have current mirrors, current mirror branches, wide ring cascodes, differential pairs, voltage references, etc. Yeah. So yeah, this is the scope of the problem. If we look, of course, this is not a new problem, but if we look at the existing tools, and specifically the commercial tools, they are typically library based. So they depend on the existence of a set of a preset library of structures that can be recognized. And these methods are pretty rigid. So if you have a small change in the structure, you have to write or add a new variant into your library. And this gets to the second problem. These libraries don't typically cover all the structures that are imagined by our designers in the different groups. And they're a bit tedious to add to, especially as the number of variants grows. Another problem is that many of the commercial algorithms are application specific. That is, they are tied into another tool, such as an optimization algorithm or a placement and routing algorithm. And we are not, it's not possible for us, at least legally, to retarget the structure recognition algorithm for our use case. As a result of this, most of this structure recognition is done manually by the front end or schematic designer. This is tedious and error prone. I showed a simple example in the last slide, but in general, these structures might span multiple sub-circuit levels. And this means they are pretty difficult to be caught or covered entirely by a manual, by a designer. Yeah. So our idea here was, let us look what we can do with a machine learning algorithm to automatically perform this structure recognition. And since we are doing this in-house, we have access to our own designs and schematics, and we can then train this algorithm with the designs from our own design teams. So I'll go in now to the feature extraction, and for each circuit, whether this is a training circuit or one of our final test or application circuits, it will go through the same extraction flow. So we take the circuit, we flatten it, and we extract first some circuit metadata. This would include it's an array of number of devices, the number of the categories, such as the number of NMOS, PMOS, resistor devices, etc. The models that are used. So for example, you have IO models, low voltage device models, etc., and the number of nets. Then for each device in the circuit, we extract some device properties, which include, for example, for MOSFET device, the channel width, the channel length, the device width, the model name, and the device category or type. All of this information, at least the values that are categories, for these we always use a one-hot encoding, right, to convert from a label to a number that we can put in a vector. We also extract a vector of what we call net encodings, which we found useful for the algorithms. And this means, again, for example, for a transistor, the gate is either signal, power, ground, maybe enable or digital. Yeah? And we encode this, the terminal net encoding as a second vector. And last but not least, we extract the adjacency matrix or the connectivity graph for the circuit. This means that you have the number of rows and columns equals the number of devices in the circuit, and you have a 1 or 0, depending on if two devices are connected. So for the structure recognition flow, well, after we extract the circuit features, the first thing we do is we pass the circuit metadata through a regression model to get an estimate of the number of structures in the circuit. And I'll visit the regression model in a following slide. This is just the overview here. We then take the number of structures recommended by the regression model. And we take a feature vector comprised of the device properties, the net encoding, and well, a column per device from the adjacency matrix of the connection graph. And we apply k-means clustering, which is just a non-parametric algorithm or method that will cluster the devices in the circuit into one, two, or more groups. The output of this is that we have clusters. Each cluster can represent a structure in the circuit. Now we could stop at this point because actually this k-means clustering also gives you a suggestion for the number of structures. However, from our tests, it's shown that this k-means clustering lacks a lot of accuracy in terms of representing the connectivity information between the devices in the circuit or the nodes in the graph. Especially if a structure is comprised of two devices that are not directly connected with an edge. Therefore, we only use this as a pre-step for our GCN. We take the device closest to each cluster center or centroid from the k-means clustering. We keep its label, so we say, and we discard all the other labels. So if in this example we have 3 clusters, we take 3 devices and keep their labels. And we take this information with the rest of the features, its device properties, etc., and pass it to a GCN. Now, this GCN is trained on a single circuit with this information until its loss function is converges or saturates. And whatever we get out of this GCN is then the final structures that we believe exist in the circuit. We then can overlay this information on a schematic with a nice GUI for the user to review the results or even edit them. So this is the overall flow. I'll just concentrate on 2 items. The regression model, this is pretty basic. We take the metadata. We have a nonlinear regression function that should give us an estimate for the number of structures in the circuit. This is an example. I think this was a DAC trim circuit. The number of structures should be 3. So this is one sample point. To get a good estimate, of course, you need some tens or better hundreds or thousands of training circuits to make an accurate model. You also have to have a robust regression to take care of outliers, etc. But this is easy. I think you can just use one of the built-in or available Python packages. This is just visualized with one of the input dimensions on the x-axis and the number of structures. And you can see in this example, there are 2 outlier circuits. Yeah. And as I said in the last slide, we take this regression model to estimate the number of structures. Now, the last but not least is the graph convolutional neural network. The purpose of this is to extract and encode the node information or update it from its neighbors. We have a nice convolution function that seems to be more accurate, up to about 30% compared to some state-of-the-art or standard library packages. The function is in the paper. We have 2 layers, the convolution, and we have the rectilinear activation function. And finally, we have a classification layer. And this is all implemented in Python, I think was TensorFlow. Yeah. So this is the algorithm. I will then just give some results. The first results here are for this regression model. Unfortunately, by the time of the DVCon paper, we only had 25 training circuits in 2 technologies. I hope we are going to remedy this for the next publication. From this, addition to this, we build the regression model based on these 25, or fit it to these 25 circuits, then apply it to 4 more circuits here. 3 OTAs, so operational transconductance amplifiers and a comparator. This is the value, the predicted number of structures from the regression model. This is the actual value that you do by, well, the designer gives us that what he believes are the correct structures. If you take the difference of these, absolute difference, and round it, because of course number of structures has to be an integer, you get some error. Our error up till now was confined to less than 2. Ideally, you want this error to be less than 0.5, so it rounds to 0, and you have an accurate, at least you have an accurate guess of the number of structures before you go to k-means plus GCN. So one point we have to do, or we're working on, is to increase the number of training circuits and have a range wide enough to cover all the examples we have at the company, since 25 is insufficient. Finally, for the application or the final structure recognition, well, these errors in the regression model will affect the next steps, but we made a workaround. So instead of just taking the predicted value from the estimated number of structures, which is the central column here in red for 5, 9, and 6 for our examples, we also do take a range. So we say it's probably between plus minus 2 of this average. So now we have a range for the estimated number of structures, for example, for this OTA of between 2 and 6. And we apply the following steps in our flow, the k-means and the GCN, to all 5 of these examples. Yeah. And from this, we give the choice to the user with a nice GUI to choose the best structure of the best representation of the structures in the circuit. If we only look at the central column, so the estimate, then the accuracy is pretty low. So between 65 and 96 for these 4 examples, which goes back to my first point here: errors in the regression model estimate affect k-means plus GCN accuracy. However, if we do this application for this range of 5 elements per circuit and let the user select the best of them, then most likely you get a very accurate output, which is going in this for these examples between 96 and 100. Accuracy here is defined as the devices that are correctly predicted to be in the correct structure over the total number of devices. Yeah. And hopefully, as we improve the regression model, we can either reduce this range that we have to give the user, or we can throw it away because we always have a very accurate regression model. This is what I wanted to give for result. And as a conclusion, structure recognition is a step needed in constraint-driven design and many design automation applications. A flow was presented here. The k-means plus GCN steps actually give a nice way or to perform structure recognition. The only drawback that we have here is the weak point, which is this regression model, where the accuracy must be improved. And therefore, of course, our first next step is to improve the accuracy. But also, there's one point that I didn't bring up in this presentation. I just talked about that we recognized the structures. I didn't label the structures as a differential pair or current mirror. For this, we are developing a second GCN that is able to take the results of this structure recognition flow given today and then label the function of each of the structures. And hopefully this will be published soon. Thank you very much. I think I'm in time.
You're certainly in time. Husni, that was an excellent presentation, for me, a very clear worked example of this machine learning stuff, of which we're seeing quite a lot, especially, for instance, the vector extraction step and how you went about that. I hope we're going to get some questions. Everyone, please type your questions just into the chat window. And for the moment, I'll give you a question to get started here. I was just curious if you have this manual selection process at the end from the reduced set of candidates, and you get the designers involved. Does that in some way feed back to the learning of the whole mechanism? Does that information somehow improve the algorithm?
It's a very good question. Thank you. Yes, it does. With the permission of some designers, we record the changes or the edits in our GUI. We then use this in the future, first of all, to improve our training set. And also, when they apply our algorithm to a new circuit, this is also automatically recorded in our database so that we can use it for further training or as a test circuit. Of course, you can imagine for some design teams, they don't want an external tool or person not from their project recording or taking this information. But we do have some teams that are cooperative, and they see the future benefit from this.
Mm-hmm. I'm not seeing any questions. Oh, here's a question from Imana. How do you identify the boundary of your circuit structures from a sea of transistors? Is it done by a human or by your?
I don't think I understand the question, but in general, the user is allowed to give a whole IP that also has some digital blocks such as gates in there as input. We've also added, for instance, digital gates that are created as part of an analog circuit as some of the structures that need to be recognized. So if the user added in the schematic some logic or some registers, then these also should be recognized by our algorithm. We also have some pre-processing to label blocks, for example, as digital or not interesting to our tool. We do this usually by the name of the cell or the library from which it is taken, right? So in this way, we can throw away some information during the pre-processing step. If the question was about the training or how do we get the training data, it's actually a lot of effort to label all these circuits if they're not already labeled, right, with the different structures, and also to chase the designers maybe to review this for complicated examples where we're not sure if this is a voltage reference or part of something else, for example. I hope that answered it. I of course, could have a follow-up.
Yeah, or any other questions? In the meantime, maybe I have one question. As primarily a digital guy, could you give us a nice clear example of where the structure recognition is needed in the analog domain?
So one tool that we use is Cadence Virtuoso. It's a commercial tool. And this tool has built-in constraints manager. You can define in this manually, usually, constraints over a bunch of transistors. And these constraints are then read when you do placement and routing. So when you place the devices in the layout view. Then can be done in a certain way. So it can then put the devices with dummies around them, right, to avoid mismatch. So this is one application. The other one is we use an optimization algorithm for automatic circuit sizing. In that case, this algorithm is it's sequential quadratic programming, and you get much further with this tool if you also define electrical and geometric constraints. So if you know all your devices should be in saturation and strong inversion, right? Then you give this as an electrical rule that translates into electrical constraint. And yeah, this is then taken by the optimization algorithm as a constraint, and all constraints have to be feasible before you look at performances such as speed or bandwidth. If that was
okay, we have another question here. What hyperparameters have you been what hyperparameters have you monitored in order to validate your models during the machine learning development phase?
Ooh, I can't answer that one. Sorry, I don't understand the question, but I can answer it later on.
Or maybe, yeah, I guess we're kind of out of time. Yeah, we're pretty much out of time. But of course, everyone can get a hold of is it Habal or Husni?
Husni Habal.
Oh, okay, Habal, okay, Husni. Okay.
Don't worry about it.
Yeah, I'm not too worried, but I hope I haven't. But anyway, yeah, everyone can get in touch with the author as usual. And thanks again, a round of applause for your presentation.
Thank you.
Okay, next up, we're going to have a presentation entitled Democratizing Formal Verification. And the presenter here is Tobias Ludwig, or
Yes, correct. Ludwig. Hello, everyone.
From Lubis EDA or EDA. Okay, I'll hand over to you, Tobias.
Thank you very much. I think we should turn off the video during the recording. Is that correct?
I can, yeah. You have to share. Yeah.
Oh, what's going on here? Yeah. Hello, everyone. Welcome to the presentation called Democratizing Formal Verification. I'm really happy that we have that many people listening at the end of the second day. I know it has been a long day for most of us. What I present today should be like an easy presentation. It's a new idea that how we can improve verification process by applying formal verification in a wider audience within the company. And yeah, I will present today how we could achieve that goal. If we take a look at the history of formal verification, everything started back in the 70s with a crazy theoretical approach called theorem proving, mostly conducted by people that are working in research or math PhDs. And it was not really applicable to the field of digital design. That changed early 90s when theorem proving evolved and people started using something called formal property checking. And yeah, until about 10 years ago, I think formal property checking was mostly used by expert. Yeah, you had to have a good knowledge on how the models in the background work. You had to write the properties by hand. And I think most people that work in this field have some kind of PhD in the area. That changed when the formal companies started, trying to bring more formal to the field by having automated formal apps. I think there's quite a bunch now out there. Almost all big vendors have some formal automated apps to some sort. they did a great job at widening the audience that could use formal without the knowledge of really understanding what's going on under the hood and without the need to write the properties. However, we're still missing out a lot of potential here because we could even have more people working with formal. So what I will propose today is a new idea and something that I think doesn't exist in the field yet. That's the core idea, is that we generate properties automatically. We have some kind of formalized specification, executable specification, and then we generate the properties, and the properties are the unit tests that allow us to verify our units. And I will now go through how this could work, but before we dive more into the topic, why should we actually do this? Why should we use formal and not some other technique? Well, those numbers, most people know, it's the Wilson Research Study numbers. I'm not going to read them out loud, but the key message is we need more and more time on verification. We spend more time on verification than we spend on actually designing the designs. Also, we have more and more verification engineers per team. And this is something Lubis EDA is not going to change. Also, what I present today, he won't change that. But what we would like to tackle is two sub-problems that result from the increasing verification problem. That is, on the one hand side, the debugging task. So even if the verification engineer has done a great job on writing the test benches, you still need a lot of manual effort to figure out what is actually the root cause of the problem. And I think that could be way easier if we would have a sound and abstract model. Just imagine we would be back 20 years and you would need to do all the verification that we have today on the gate level, because you couldn't trust the RTL for your design sign-off. We somewhat have the same situation today. We need to do all the verification on the RTL because we don't have an abstract model that we can use to do functional verification. Second issue is that although we have good verification, still the reason for delayed projects is 50% missed functional flaws. So bug escapes cause some kind of stalling in the development process. And I would like to add another verification technique, namely formal verification, to detect more functional flaws and reduce the number of functional flaws, and thereby, of course, reduce the amount of delayed projects and respins. So what I will propose today is an idea methodology backed by tooling that provides three benefits. We have some more certainty because we have a well-established relationship between the different models, so we can save resources and avoid respins by finding bugs. In the end, everybody is happy when he reaches the coverage goals, and reaching the coverage goals in time can be challenging from time to time, especially when the state space becomes really, really deep for designs. And lastly, to make such an approach work, we need some automation, and I will present an idea how you could automate such a flow. So what's the general idea, or what am I talking about here? So let's assume we have our regular simulation-based verification environment, either the UVM or some in-house tools. And in the end, what you always need is use cases, some kind of reference model, our design under test, and then we need a simulator to run everything. And today, everyone is happy when you run the use cases, you hit your metrics, and you verify that something works correctly. However, reaching the metrics becomes harder and harder because the design under test becomes more complex. I propose something else. I think we should have trusted and sound reference models that we can use for verification, because then we can, on the one hand side, shift left the verification to higher abstraction levels, but we can also use the more abstract levels to drive the covered metrics to the point that we wanted to. And I would like to hook into the existing flow by reading and parsing such reference models and generate a verification IP. And here we get to the point that we have the democratization of formal verification, because we developed a tool that allows you to generate the verification IP based on formal properties that almost all designers and verification engineers can use throughout the design process to verify their designs. All you have to do is generate a verification IP, load the design into the formal tool, and then verify formally that your design works correctly. And the good thing is that the verification IP now establishes a link between the reference model and the RTL design under test. And at that point, the reference model becomes a trustable model that you can actually really use to do functional verification of your design. What does that mean? So let's say we have such a reference model of a bus system, and we correctly verify with many, many use cases that we can send a message across the bus. And that always works. You can show for all use cases, we have a really high coverage that this message is sent correctly across the bus. Then we also know that because our reference model has a meaningful relationship to the RTL, that this will also be true for the lower levels. And that allows us to really easily search for those system level integration problems, because the functionality of the module will be covered by the verification IP. So the first goal is to shift left the verification and start verifying early with abstract models. But today I would like to talk a little bit about on how we establish this relationship and how we can do this by using formal verification. And what we do is we start with an executable system level description. Mostly we use systemc, but we would also be open for other kinds of input languages. We also have a graphical user interface. And the main task is to extract the abstract finite state machine from such a system level model. And you don't only want to do a one-to-one translation of a finite state machine. Sometimes the finite state machine is not there. It's just implicit. If you think of TLM interfaces, you cannot really see the state machine, but it's still there. And you want to have a minimal state machine, because that state machine will be the basis for your verification IP. So from an abstract reference model, we can generate the verification IP. And that happens in a deterministic way, so you can really understand that the connection makes sense and helps. And the verification IP itself is composed of system Verilog assertions, formal properties that are really easy to read. And they document the design intent. So what should the design actually do from a functional point of view? Of course, we lose some detail because we have abstract models. And they completely coverage the functional behavior of the design, meaning that once we're done with the process, you cannot change a line and change the functionality of the RTL without the verification IP indicating the wrong change and that something goes wrong within the verification IP. That, of course, is a pretty strong statement, because then you can actually go on and refactor your code, search for deadlocks, dead code and unreachable code, or just rename and refactor stuff without being afraid that you break the code. How does it work in practice? So let's say we successfully extracted this kind of finite state machine, and now we have our internal representation. However, as you may know, the RTL design can be way more complex than an easy, simple finite state machine, as you also sometimes find them in the specifications, right? The RTL can have, or will have, way more states than an abstract finite state machine. And what we actually want to prove is that if we can transition between the abstract state and the finite state machine, so let's say we can go from read to write here, we also want to have this transition in the RTL. However, that may take 1, 2, 3, 4, 5, or 100 clock cycles. That we only know once we develop the RTL, but we still want to have the same transitioning behavior between the important states. And we see here that the operation encode is actually split into multiple clock cycles, namely 3 here. So we need 3 clock cycles to go from encode to W. But on the abstract level, this is just one execution trace. There's no events in between, so we can abstract away that time. And what our tool does, or what we propose, what you could also do, is generate a property for each transition within the finite state machine. And we then use the properties to cover the transitions here. This is now some kind of pseudocode. I will afterwards in the next slide show an SVA example, but to illustrate the core idea, I would like to use the pseudocode. So the property assumes a certain start state and that some trigger conditions apply. And then we want to prove that in the end, we set the output to the correct value. That is the value that we received at the beginning in the read state of the operation, and that we encoded the data correctly. and we want to prove that we are in a correct ending state. If that is the case, the property will hold, and we know that the design behaves as described by the functional spec. But also we already see here that as soon as you want to start proving a property, we need to provide a value for n. So we need to know how many clock cycles should it take to go from R to W. In real life, things, of course, don't look that clean and nice. So this is now a valid SVA syntax property. And we can see here the same trigger. So we on state R, our trigger is sent. The names here are a little bit different. And we see that the end sequence is actually provided as a parameter to the property. You only need to do this once. And then you can just use the property out of the box. But in the end, we want to prove that we end up in W and that the output is set to the correct value. That is the encoded data that we receive at the beginning of the operation. But what I would actually like to get to is some concerns many people have when it comes to that idea that, yeah, we're missing many details when we have an abstract asynchronous transaction level model in the beginning. We're missing details that are only visible if you're at the RTL. And how we cope with that? Well, all the objects that result from the abstract model are represented by functions. And the main task, or the only remaining manual task that you have to do, is to refine and fill out this function and say, okay, how are things actually implemented in the RTL? So let's say the data that we receive at the beginning of the operation is a 32-bit integer. And of course, you could have a 32-bit wide input port in the RTL. In this case, passing data would simply be refined to the RTL signal. But in practice, things are not always that easy. So let's say the data is received sequentially and we receive 8-bit packages over 4-bit cycles. This is, in our experience, a pretty common thing that happens, that you have sequential transmissions in the RTL, whereas in the abstract model, we just want to say, okay, give me the data. I want 32 bits. I don't want to have 4 events triggering for that, because that will cost me simulation time and will make my whole simulation more complex. So in this case, we need to provide this information to the function and refine the function such that it copes with this complexity. And we see here that the 32-bit are actually composed of the last 8-bit packages that we received within the last 8 cycles. And such a refinement has to be done for each object from the system level. The good thing is you cannot really make a mistake here. If you make a mistake here, one of the properties will eventually fail. Yeah, but how does it work in practice? Now we have like this refinement thing and we have the abstract model. In the end, what we want is we want to prove the verification appear in the RTL design. And I would like now to explain a little bit how does it work in practice by a small and simple example. So let's say we have our reference model. We verify the reference model that works correctly. So the system works correctly. And now we are at the step that we want to generate our properties that can be seen as some kind of unit tests for the block that we want to verify. And we want to run these properties on the design. And let's say the extracted state machine looks like this. And I'm going to focus on those 2 transitions here, check to wait, check to done. We see here the trigger conditions. Then depending on what X is, we either take the one transition or the other one. And it's quite important to note that those trigger conditions perfectly overlap. So let's say this one here would only be X is bigger than 0. Then we wouldn't have something specified what should happen in the design if X is equal to 0. And this is one of the things that makes our property set complete and full and allows you to fully coverage your RTL design. So there's no gaps within the properties. They completely cover the RTL design without gaps. As I said earlier, we generate a property for each transition, and the generated properties look like this. Here again, the assumption that we start in state check, that X is less than 0, and that we transition to state done. And we start in state check, that X is bigger than 0, and we ended in state wait. And now we run the properties on an RTL design. Let's say it's really simple and small, as you can see here. And in this case, we will see that the checked done property will hold, because anytime x is less than 0, we would transition to done. And of course, if we run the second property, that one would fail. You may have already seen it. If x is equal to 0, we transition to done. However, from the functional specification, we should actually transition to wait. And this is one of the main reasons why I would like to bring formal verification as part of every verification flow, because formal verification is really, really good at finding these one-off corner case bugs. And also, if it finds a bug, in most cases, the formal verification tool will provide you a minimal and small counter example that shows you how you reach the bug, what input sequence leads to the bug starting from reset. So you don't have to go through thousands of clock cycles to see the root cause of the bug. It presents you a minimum counter example and trace of the root cause. We've been working with this technique now quite for a while, and we realized when we have a sequential design, this idea works really, really well. However, when it comes to pipeline designs, we tend to see some issues, because then multiple transitions are active at the same time. So we adapted a technique that is called SQRQD to our needs, and also adapted the way we generate the properties. And here we have a little bit of a different proof idea. So we generate two different kinds of verification IPs. The first one we call the base properties. And the base property has a special assumption. It works for all kinds of pipelines, but let's stick with the example of a processor. So the base property would assume a flushed state, and the first token, so instruction, is propagating through the pipeline. And the base property will detect a bug within a single execution of the property. So let's say, stupid thing, you did something wrong with the decoding, and the add instruction is actually interpreted as a subtract instruction, and you end up having the wrong results in the register. In this case, the base property would fail and would flag the bug right away. But since we assume that we start from an empty pipeline state, the question remains, well, does the instruction actually work with a pipeline that's filled with instructions? And for this, we generate a completely different verification IP. And that verification IP assumes that there are two instances of the design. One is the simple constraint instance, and the second instance is free on its initial state. So it can have any kind of instructions already loaded in the pipeline. And this property proves, by making another assumption, that those two instances behave the same if the same instruction is loaded for the design. And if there is, for example, a problem with the forwarding of the design, the relax property will fail and will pinpoint you the problem and saying, hey, for this case, if those instructions are in the pipeline, those two instances behave differently. And that allows you to find all kinds of pipeline-related bugs. And it also allows you to kind of play with your pipeline and see if you can fine-tune it to find even more potential to optimize your pipeline. Yeah, I have 3 case studies here, 2 with a pipeline, 1 classical sequential design. I will just quickly run through the results and highlight what makes this approach actually attractive and why you should use it within your company, and how the formal verification can actually help with your verification efforts. So the first one is a RISC-V processor, formerly known as Risky, now part of the Open Hardware Group. The new name is CV32E40P. We did build the reference model for it and generated the properties. But before we did that, we verified our reference models with the standard RISC-V test and some tests on our own. And we did rerun these tests also on the RTL to measure like how much speed effort do we actually get, because one of the goals is to shift left the verification and have a simpler and easier to use reference model. And we see here that we have some nice results for the simulation. Also, the number of the properties that we generate is totally within reason. So we only have 22 properties, basically 1 for each instruction. that we verify and one for the reset. And in the end, we end up having a proof time of about 3 hours, let's say, depending on the how much power the server has left, which is still okay if you think of overnight regressions. And the good thing about formal is if something is wrong with the design, usually finding the counterexample and making the property fail is way faster than proving the property. So if something is up, you will get usually a counterexample real quick. Second design that we did was an AHB bus. We verified single read, single write, burst read, burst write here. Again, we did the same thing, electronic system level simulation, RTL simulation for random input stimuli. We have a little bit less properties here. In general, I would say, if you want readable properties, you should not generate more than 50 properties. If that's the case, you may want to split your reference model into 2, because at some point, the properties lose their documentation character, and then you lose much of the benefit. Again, here, reasonable proof time. We are almost at the lunch break time, so you can let it run over lunch break and get some results. Lastly, this is just a sequential design. It's not pipeline, but I still wanted to put it there because this is probably one of the sweet spots of the entire idea. When you want to use formal, it's a really control dominant design. It's a solid SDH framer with little computation, so little data path components. And here we get a really, really big abstraction regarding lines of code between ASL and RTL, but also big abstraction for the simulation. And if you have control dominant designs that are typically hard to verify for simulation, using formal verification is great benefit. And we see this also by the numbers of the proof time. The proof is really fast because the model is quite small compared to a processor model when it needs to prove all the arithmetic computations that are going on. I'm almost at the end of my talk. I hope you got inspired a little bit how we could make use of formal verification within your verification flows. I think with a tool that, like we offered Lubis Veritas, the design and verification engineers can benefit because they can use formal verification, and we will lead to faster design cycles if such a methodology is adapted. And actually, you don't need that much things. You need something that generates the properties for you, and you need any state-of-the-art property checker that can work with SVA properties. And then, we can democratize formal within your company, and you can shift left the global design verification task and get your system level verification done faster. Thank you very much for your attention, and let me know what you think, any ideas and feedback.
Okay, does anyone have any questions? Could you just type them into the chat for Tobias? While you're doing that, I'd just like to thank you, Tobias. Very excellent presentation. I like it.
Thanks.
A lot of food for thought, maybe I'll just ask one question, because again, towards the end, I think as well, we seem to focus down on sort of minimizing the scope of the problem to get the best of the results somehow. How do you handle, let's say, higher level conceptual property of a design? It's not just a cluster of low-level functions all correctly bound together, but at the end of the day, it still has to fulfill the application. We kind of get that by accident, in general, with the simulation world. It's not that it's particularly great at it, but it is certainly the case that it can get dropped by accident down the gap when we go to too low a level of abstraction. How do you just see these things working together, the simulation and the formal, or do you have any special tricks for that?
No, I see it working together. First of all, I see the idea that I presented today as an on-top thing that you can use on the verification that you already do. And I'm not sure if I got your question completely right. You're asking about what you do if your reference model is so abstract that it doesn't really relate to the RTL anymore. Was that the
No,
question?
it could be correct. but too low level, you know, where it's extracted correct subset of the things, but not necessarily the overall intent.
Ah, I see. So yeah, I always say we should not rewrite the RTL in our reference model, because then we don't gain anything. We should actually think of what's the product machine of my RTL, like what's the most abstract level I can go to before the model loses its meaning. And that's the point we should start. I agree. If the abstract model is too low level, then we don't gain anything, and we just have overhead of rewriting the RTL.
Marky simulates that abstract model, so that does exactly what you're thinking of with the that you verify the intent, not the implementation. So
yeah, it's sitting kind of on top, right? Not instead of, yeah. Okay.
So with the model, he would do the stuff with, like, you know, this machine is supposed to do this. When I do that, and after this, these registers should get updated like that.
Okay. Thank you, Toda. Any other questions? I don't see anything popping up in chat.
Oh, there's one more.
Yeah, there's some there. You want to go straight in there, take it? You see it?
Yeah, I see it. Yeah, liveness. On the abstract level, we are back to simulation, and the core idea is that the abstract level is abstract enough and simple enough that you can actually, get a really, really good coverage of simulation-based approaches. Of course, you could basically turn the abstract model into something that a formal tool can read. I think some of the big formal tool vendors now allow you to pass, for example, system C descriptions, and then you could write the liveness property there. I mean, I guess the question relates to, usually the liveness property doesn't like converge because the state space is too big. But if you have this simple abstract models, you have a good chance that your liveness property can actually hold on such an abstract model.
Okay, I guess there's no more questions at the moment. We're kind of out of time anyway. So once again, I'd like to thank Tobias on behalf of everyone here. And as Ma reminds us all for here, and of course for the last paper, please remember to vote for best paper. The link's there in the chat, but it's also, of course, available on the DVCon site elsewhere. But yeah, let's remember and vote for these guys after all their hard effort. Yeah. Okay, let's move on to the third paper in this set. And this is from Jamie Hanlon of Graphcore Limited in the UK. I'll pass straight over to you, Jamie, and you can take it from there, okay?
Thank you. Can you hear me okay? Can you see my slides? Cool.
Yeah.
Great. My name's Jamie from Graphcore in the UK. We're a company that builds systems for accelerating machine learning workloads. So a big part of what we do is designing large ASIC chips, that have huge kind of floating point capability. The talk today is about a tool that's kind of grown out of a side project, some of the work that I've been doing at Graphcore for front-end netlist analysis, which I'll explain in a minute. Right, so to give an overview of the talk.
Sorry, Jamie, we're seeing your whole view here, not just the final slides. We're seeing your whole presenter page here.
Oh, really? Okay. Maybe I can share this one.
Yes, swap display.
That's it. Yeah.
Is that better? Cool.
Yeah.
Okay. So some context about what the problem is, how we solve the problem currently, and what this tool is, what it does. A couple of application examples, so where we've used this to good effect at Graphcore, and kind of a wrap up. So modern RTL designs use a variety of tools from a variety of vendors to assist in all aspects of development and debug. So the tools fall into categories of simulation, linting, power analysis, synthesis, CDC, clock domain and reset domain crossing analysis, formal verification. But it's worth pointing out that developing custom tooling and flows using these tools or other means can provide ways to further enhance RTL development. Particularly when chips have particular sort of unusual aspects of their design. And I suppose a crucial part of all of this is that fast feedback to designers improves productivity. So where something can be run quickly without having to push it through lots of particularly the back-end physical design flows to get feedback on critical timing paths or power issues early on, speeds up the whole design process. So in terms of building custom tools and flows, when you look at the standard offerings from the EDA vendors, their tools are proprietary and licensed, which makes them which makes the availability of those tools scarce within an organization. And almost always they provide a TCL kind of API, which is difficult to integrate with other languages. And in particular at Graphcore, we use Python for almost all of our infrastructure and glue logic for everything. So, and it's difficult for us to interface Python to Tickle. We do it, but it's not without some pain. So the observation from my point of view is that there's a lack of a simple generic tool that provides access to a source level netlist model. And so what I mean is that, rather than looking at the design as it is when it's synthesized and in gates and all of the design data that comes along with that, but just a tool that can allow you to query what's in your design, what types, and the structure and connectivity of it. And with that information, I think you can do some useful things. So yeah, to speak a bit more about what you can do with current tools out there. So in the simulation category, you've got tools like VCS, Questa, Xcelium, and I would observe that their TCL interface are designed around driving the tool, but not really providing access to the underlying model of the design. There's one sort of minor exception to this, I think, which is Synopsys provide what they call their native programming interface, which does provide access to the data, to the underlying data structures through a set of models. So for instance, for the source code model or a netlist model, or there's a structural coverage model. But each model has limitations, and I've played around with those models, and they haven't quite provided what we've needed. In the synthesis category, you've got tools like Fusion, Compiler, and Genus. And you can elaborate the RTL to learn about its structure, but the source code correspondence is degraded. So it's hard when you're looking at the gates of the netlist version to correspond that back to where combinatorial paths traverse through the design, for example. There's an interesting set of open source tools, and open source tools can obviously be modified and repurposed. And just to point out some interesting ones, so parsers include Veritable, which is a Google project. There's one called Slang, System Verilog Language Services, and another impressive project called SureLog. They're mainly focused around parsing and linting, designed for building tooling, really. Yosys is a notable mature synthesis platform, primarily intended for FPGAs. And in simulation, you've got Verilator and Icarus. So to introduce this tool that we've built, it's open source, and it's sort of built as a library for source level netlist analysis, as I've described. And we have leveraged Verilator to do what we need to do. So what it does is it runs Verilator, and it gets Verilator to produce an elaborated, flattened netlist of design, and that's produced in an XML format. In order to get Verilator to do that, we did make some changes to the Verilator source code. In particular, to get it to flatten the design. So this is where it inlines all the modules, and you end up with a single module with all of the design instanced in it. Then it takes the XML, it reads it, it works out where variables are, it works out where the data dependencies are between the variables, and it creates a directed graph as its main internal data structure. We've implemented this as a C++ library for performance, but we provide two means of interacting. So a command line interface with interactive use, and a Python API wrapping all of the C++ API for integration into our own scripting and infrastructure. And as I've said, we've used this successfully at Graphcore in our work in developing high performance ASIC RTL. So just to say a little bit more about what the view that Netlist Fast takes on design and how it processes that XML. So here's just a very simple example of an adder module. Takes two inputs, produces a sum and a carry out. So in the middle of these two is the XML format. It reads the XML and it produces the directed graph on the right. And so each arrow shows a data dependency, and the nodes represent either variables or logic, so kind of statements or expressions in the source code. And you can see here that each of the two outputs, the carry out and the sum, are dependent on the two inputs, as you'd expect. A slightly more interesting example, this time with a register. And what it does with registers is it splits them into two parts. And this is useful when looking at paths through the design, and particularly because timing paths in the physical design start and end on ports or registers. So a register, as you can see here, has a source and destination component. And in the top part, the top graph, you can see the nodes are the logical fan-in cone to the data queue, and that takes the input and the clock and reset, which are part of the always FF sensitivity list. And then the bottom, you've got the logical fan-out of data queue, which is an assignment to the output variable. So yeah, so this is really the sort of the main data structure and that Netlist Fast builds. So just to sort of outline the features of the API, so you can look up variables and data types. You can match these exactly or with regular expressions and wildcards. You can query paths, and I'm going to give an example of this in a minute to explain that. But you can look at paths from point to point. You can look at fan-out paths or fan-in paths, and you can also choose to have paths run through registers or start and stop on registers. And you can add constraints to refine path queries to establish correspondences with other tools. And the reason that you need to do this is because between any 2 points in a graph, it's generally computationally infeasible to enumerate all of the paths because the number of paths grows exponentially with the number of nodes. And yeah, I think I should say that these set of features is kind of inspired by the kind of functionality that's provided by tools such as Design Compiler and ICC. But as I said, it's in the front end domain, it's in the domain of the source code rather than the gate level netlist. Okay, so to make this all a bit more concrete, first application is looking at critical timing paths. So what I've got here is a kind of reasonably truncated timing report. It's a lot longer than this for a real timing path in one of our designs. And things to point out here is that you've got a register start point, you've got a register end point, and you've got a lot of intermediate cells in that. And most of them have automatically generated names. This is because the design is highly optimized, and much of that original source correspondence is lost. I've highlighted two original source names, which are useful, as I'll explain now. So, when you're looking at this timing path and you want to attempt to fix it, you need to work out where it occurs in the RTL. And so, using the command line version part of this tool, you can pass it the netlist which you've compiled, the XML netlist, and you can specify the start and the end point, and you can direct it to go through those two intermediate net names. And because of the way that the backend tools flatten names by removing hierarchy and inserting underscores and adding register bits and things, there's an option here to ignore those hierarchy markers. If we match by regex, we can match portions of that name. And so what that returns is a path from between those points and going through those intermediate nets. And so again, it's too much to fit on the slide, but what you have here is a complete description of exactly where that path or how that path traverses through various different modules. And this is something that we've found really useful for diagnosing timing issues. What it also provides you is a way to quickly validate your fixes. So using this tool and using this view, you can look at the RTL, you can go in, you can change a condition, you can recompile the netlist, rerun the command, and if you've broken the timing path, that a path will no longer exist. Rather than sending the RTL patch to the physical designer, rerunning the build, waiting quite often a day for a result to come back, and going from there. So second application where we've used this is structural unit tests. So the motivation here is that it's common practice to generate top-level integration RTL. And early development of this RTL is often done without verification support. And whenever you're dealing with a top level of a design, it's a long process to bring the verification up. And once it's there, it's expensive and slow to run simulations, and it's not. You don't want to be debugging basic issues in design, through the verification simulation test bench. So to mitigate these problems, what we've done is use Netlist paths to just implement some very simple connectivity checks to just validate that things are as we expect. And this has picked up basic issues, and it has allowed us to run ahead of the verification and have confidence that all of this thousands of lines of auto-generated RTL are in fact connected in the right way. Yes, and as I've mentioned, because it's a Python API, because all of our infrastructure is based in Python, it was very quick to develop something like this. So here's an example of a kind of a top level. So you've got a set of routers that have interfaces connected between them, and each router is connected to a client. And the Python to write such a unit test can look something like this. So you import netlist pass as a Python module. You can set some options, load in the netlist XML, and here we're just checking that each router is connected to the next router along. So you look at each of its interfaces, and and you set up what the expected signal names will be, and then you use this API call that a path exists between those 2 points. So kind of simple but effective. As I said at the beginning, there are tools that allow you to do this kind of thing. And we played around with using Fusion Compiler to do this. And notwithstanding the issues with integrating or interfacing with TCL to run Fusion Compiler, it's a lot slower. You know, there's quite a significant overhead to starting it up. And you can see here that you know, for 4 up to 64 routers, you know, Fusion Compiler is running in yeah, a significantly longer time than Netlist paths. And so what this allows us to do is, you know, we can quickly develop these tests. We can add them to the CI test suite with a minimal impact on overall runtime. You know, and we're not adding to any license contention with Fusion Compiler. So we have used this for other applications at Graphcore. So one of them is checking of patterns that match design objects, and this is for quality of result reporting in the physical backend. So rather than have ad hoc patterns specified in TickleScript, which are owned by physical design, what we've done is we've moved them all into the front end. We specify them in Python, and we use Netlist paths to check them against the design. So we say, you know, does this register exist? Does this port exist? Is there a path between these 2 points? And what that does is means that those patterns are maintained with the development of the RTL. Another one is using it for catching simple CDC, RDC violations. And we've also used it in producing documentation for designs. So yeah, to summarize, we've developed a tool and a library that's lightweight, it's open source, and it provides access to a source level netlist. It's very simple, but we've deployed it to good effect. It allows simple custom tooling to be built in Python, and it's easily integrated with existing Python infrastructure. In our application examples and use cases, you know, the main benefit to them is that they've provided faster feedback to the designer, you know, which is improved productivity, and yeah, simplified team interactions. Yeah, this was joint work with Samuel Kong at Graphcore, so just an acknowledgement and the hard work that he's put in. And thank you, and I'll take any questions.
Oh, thanks. Thank you, Jamie, for that presentation. Oh, sorry, my video's coming on and off here. Do we have any questions? Could you type your questions into the chat window for Jamie? Let's see. Well, here we have a question from Tobias there. Do you have any problems with the tools, your tools, I guess, regarding supported language subsets?
Yeah, that's a really great question. So
do you handle the interfaces correctly?
Yeah. The good thing about focusing this on synthesizable system Verilog is that it's a very small language subset. I pointed out a few open source projects such as Variable and Slang that provide Verilog front ends, but it's surprising that I've tried them and they're not all compatible with our code base. Yosis, for example, only supports Verilog 2005. So yes, it is a problem, and yeah, it's surprising that there's still quite a disparity between the tools. The principal reason why I've chose Verilator to build this upon was that we were already using varilating simulation, so we knew it's compatible with the code base, and within the open source EDA tool community, it is a very mature platform. So yeah, it was a good option.
Yeah, I agree. I was just wondering, because we're also looking into open source system Verilog parsers. There are some out there, but I would be afraid to choose one because the language is quite complicated, and apparently even the big EDA vendors sometimes have problem understanding the language.
Yeah. There's a very good website that's maintained by the YOSIS team that reports all the system Verilog compatibility with the various open source tools. So that's worth checking out. But I found that they can even fall over on some quite simple stuff.
Do we have any other questions? We still have time. I'll ask a question while we're waiting for the next one to come in there, Jamie. So this contribution of yours is open source as well. Does that include various patterns for the types of checks you might want to instrument in your Python work?
No, not particularly. I suppose the API is designed in such a way that it's made it easy for us to implement the kind of checks that I've described. But it's, I suppose, more broadly, it has been implemented as a general API, really just to provide easy access to that underlying netlist.
Yeah.
In contrast, as I said at the beginning, that with the TCL interface, the various tools being much more geared around to driving the tool rather than providing access to the data structure.
Any other questions coming in? I don't see any at the moment. In terms of maybe another question then from me, in terms of, for instance, the connectivity checking, how does it compare with, say, doing standard formal connectivity checking, with table-based inputs and exhaustive or relatively exhaustive proofing of the network connections, although albeit I'm hearing from most people somewhat limited to digital nets rather than analog nets. Is there anything you guys can do better? Are you quicker, I guess, perhaps, but is it as comprehensive? Or is it just?
I'd expect not. And I haven't, in all honesty, I haven't looked in detail at using comparing this against formal structural connectivity checks. I think, I would just again point to really the two practical benefits for us, that it doesn't tie up licenses, it's much faster, and it's easier to use because it's all based in Python.
I guess being Python based, you can also read in tabular forms of connection rules anyway, right? And parse it.
Yeah.
So you could have the same source effectively for the connection specification. Yeah,
absolutely. And as I said, everything that we do at Graphcore is is expressed and glued together in Python. So yeah, it just makes it a lot easier. With the formal tools that we use, we have developed kind of a compatibility layer between Tcl and Python, but it's hard to maintain. It's not that easily extensible, and yeah, it's just makes things that little bit more difficult than you'd like, and kind of stops you. I think developing simple checks like this.
Okay, I guess there's no more questions coming in, so I'd just like to thank you again, Jamie, and Samuel, I guess, who wasn't presenting here. But thanks for your presentation, and I certainly look forward to reading the paper. Always happens afterwards, but I think you know that. Okay.
Thank you.
Thanks. And remember, everyone, please visit the best paper page and cast your votes, as it were. I'll hang about here, but I guess officially the session's finished, but we can hang about here, the presenters and myself, for a few minutes. If anyone wants to just chat, feel free. For the rest of you, thanks for attending. Bye for now.
Thank you very much, Mark. Goodbye.
Goodbye. Goodbye.
Yeah, thanks for sharing the session.
No problem, Tobias. Thanks for all your effort. Asma, I guess you can wrap up